Okay, so many of the ideas of relativity can be described on what's called a space-time diagram. So we want to get a sense of what this thing is. So we're not going to introduce the ideas of relativity just yet. We're going to play around with this kind of diagram, and it involves position or distance, say, in the x direction, and time on the other axis. So let's get a sense of how to describe the things in a one-dimensional universe. So let's say that I live in this one-dimensional world, so I can be at different locations along the x direction. Right, so the origin could be my position right now in this room, and there are positions to my right and positions to my left. The left would be negative directions, negative x directions, so we could sort of generalize that. And if I am not moving, so let's consider what it's like not to move on a space-time diagram. So let's say that I'm not moving and I'm at the origin, as I just said. At t equals 0, that represents my position. And if I continue to live at that location, then my subsequent positions will just be along this direction because time is passing. So this axis represents time passing at that specific location. So that's an example of a path on the space-time diagram describing the absence of motion in this one-dimensional universe. Now let's say that I instead live at x equals 10, and t equals 0 represents right now, so I'm here at x equals 10, at t equals 0, and I continue to live my life there, then the motion, my path through space-time, is indicated by that curve. So I'm just traveling upwards. Okay, so the time axis is just vertical on this space-time diagram. So there's nothing special about that time. Let's say that I want to consider living and describing my path in the space-time diagram from birth. So I could have been born some years in the past, and I was born at some location along the x-axis there. It's between x equals 0 and x equals 10, so that's my location in some this time in the past, whatever that time corresponds to. And let's say I don't live a very interesting life, I just stay at that location. Well, my path through space-time is given like that, and if this is the present, then here I am at that location, not doing anything interesting, and if I continue to live my life out that way, that's the path through space-time. That's my space-time path. The motion on the space-time diagram. Okay, so all the events of my life occur along this line. So let's consider a more interesting path through space-time. Let's say I want to move to the right. So let's say we want to move to the right, but we want to move at a constant speed. So here is x and here is t, and I want to move at constant speed. What would that look like? So I'm not, let's say I start here at t equals 0, I'm at x equals 0, but at t equals 1, I'm no longer at x equals 0, but I'm moving to the right, so I'm going to be, say, here. So at t equals 1, if t equals 1 is there, and x equals 1, right, whatever these units are, let's say I'm over here. So that represents motion to the right. And if I continue to move at that same rate, which is given by the slope, right? Distance over time, that would look something like this, where the slope is unchanging. So the slope there, or rather the inverse slope, is actually the speed of motion, right? So this represents motion through space-time at constant speed to the right. What about motion through space-time to the left? Well, let's say I move at the same rate, and instead of moving at that rate to the right, I move to the left. Well, that would simply be I move to -1 in t equals 1, and so that would be something like that. And if I continue to move that way, my slope is unchanged, and it looks like that. But there's nothing special about starting here. I could start anywhere. I could be here and go at that same rate. And so if I'm going at that same rate to the right, then I want to go 1 to the right and 1 up, and that would be something like that. I would get a line that's parallel to this one. And the same thing if I wanted to go to the left, right? I would have to draw a line here that's parallel to this one, which would be something like that. Okay, so these lines represent motion at constant speed. Of course, I can do the same thing below, to the right and or to the left. And if I want to represent motion that's faster, then I want to curve or tilt rather more toward the x-axis, because I want to travel more in the x direction than in the time direction. So I'm going to bend more toward the x-axis. That represents a faster kind of motion to the right, and that's an equivalent faster motion to the left. The bending here turned out to be a little less than this one, so this is a little bit slower to the left and this is to the right. But they're both greater speeds than these two space-time paths. Okay, let's consider accelerated motion. So maybe accelerated motion to the right. So now we've sort of generalized the space-time diagram x and t to have both positive and negative values. Let's say I'm starting here at some time. I'm at this location in space, in this one-dimensional universe, and I want to speed up. So I might travel to there. I'm traveling to the right as time is passing, but I want to travel faster and faster, so I'm going to bend more and more along the x-axis, and so that changing slope represents acceleration, right? I'm speeding up, and I could instead slow down. So if I travel, say, to the right like that, but I want to next slow down, I'm not going to have the same speed or greater. I'm going to tilt the other way, so I'm going to do something like that. I'm going to bend that way, and that represents slowing down, a negative acceleration. So we can call things that happen at locations in space at certain moments in time, like this right here. There's some t, let's call it t naught, and it happens some event occurring at x naught at a moment t naught. That's an event. So this little dot represents an event, a space-time event. This is another space-time event at some different location, maybe x1, and at a later time, which is, say, t1. Okay, so these are different space-time events, and they can be connected along the space-time diagram. So, for example, here are two events, say event A happening at some time here, t naught, say, and at some location x naught, and then maybe another event here, call it event B, at a different location, say x1 and t1. Okay, this could represent something traveling along the x direction from here to here at constant speed, and so it could be part of a space-time path that looks like that. Say maybe this is me just sitting here and you just sitting here, and me throwing the ball, you sitting here at all times, so your path through space-time would be a vertical curve there. My path through space-time would be a vertical curve there. And let's say I throw something to you, and this represents the thing moving towards you at constant speed. I throw it to you, and then you catch it, and it reaches you at t1. So that's the two events connected causally. This represents cause and effect on a space-time diagram. Let's look at the fact that, let's notice that this event is happening at t naught, whereas this event happens later at t1, so t1 is greater than t naught, right? One is in the future of the other. Let's consider another event here, event C. Notice that this event is happening at the same time, so event A and C are what we call simultaneous. Okay, so these are simultaneous events on a space-time diagram appear on a parallel line, right? So this is like the spatial axis. So when we think of simultaneity, we draw parallel lines, and these are all of the things that happen at the same time on the space-time diagram, whereas the vertical direction, these represent all of the different times at one single location. Here's a different location, all different times. Here's another fixed location with all different times. Okay, and so we'll get with these ideas in hand, we can start to derive the ideas of relativity.